One application of thermodynamics is the heat engine, where we use heat to generate work. And so we'll start by looking at a schematic of a real heat engine. So a real heat engine has some form of heat, and I'll just draw like a fire here, and we'll just call this the heat source. And the heat source could be a nuclear power plant, it could be a wood fire, it could be concentrated solar. Typically in the US, if we're making electricity, our heat source is mainly going to be coal, although locally here we have Diablo Canyon. So the heat source is going to heat up a liquid. And the fluid doesn't have to be a liquid, it could be a gas. Typically it's going to be, in quite a lot of our heat engines, it will be water, and the water is boiled over the heat source, and then the water vapor is going to shoot out of a nozzle, and we have some way of capturing that energy. So we'll have some sort of turbine. So I'll show here as something with buckets that are going to be catching this. Of course, this is just a schematic. So what's happening is that this thing is going to spin in this direction. So this could be attached to the shaft of a generator or something. Okay, so the water or other fluid is heated up. It expands. It may go through a phase change, but at least it expands if it's heated, and so that's going to cause this turbine to spin. All right, now this whole thing is housed, and so we can gather all the fluids. The fluid is going to flow down through this channel, and now it's very hot, right, because it was heated in the boiler, and so we're going to reject some of that heat as waste heat, and we could do this by just putting some fins on here to radiate the heat away. And we'll call this the cold sink, or I guess we'll call it let's call it the heat sink. That makes more sense. And the heat sink could be anything that's capable of taking heat away. So though it could be air radiation, that's the least effective way of getting rid of the heat. So the heat sink typically will be either a cooling tower, or better yet, a lot of cold water. So a river, or even better, the Pacific Ocean, right? If we have an ocean or a big enough lake, like one of the Great Lakes, we can use that as a heat sink, and that's what they do at Diablo Canyon. Okay, so we get the water or other fluid. It's now cooled back down, and we can pipe it back this way. So the idea is that in a heat engine we have a cycle. And so notice the water goes through a cycle and returns to its initial state. Okay? So that's how we would have a heat engine. And notice that we're putting in energy by burning coal or having a nuclear reaction here, and then we're extracting some of that energy in the form of work at this turbine. We can envision several different types of cycles that would match up to a heat engine, and the simplest one is the Carnot cycle, so we'll look at that. So a Carnot cycle is simple in that we put the heat in at one temperature. So we have the heat source at some high temperature, and we have the heat sink at some low temperature, so T hot and T cold. And we have our cycle in the middle, and in our cycle we have our fluid just going through complete cycles. We put some heat from the heat source, so that's going to be Q hot, and we reject some waste heat into T cold. So we'll call that Q cold. And notice Q cold is less than Q hot because energy is conserved, and we're going to extract some energy out as work. All right, so let's go ahead and analyze what these numbers have to be. Well, first, let's look at the first law. The first law says that energy is conserved. And we notice we're not changing the internal energy of our fluid because our fluid's going through a complete cycle. So from the start to the end of the cycle, our delta U has to be 0. So that means that whatever heat we put in has to either come out as heat or as work. So we can say that the heat we put in is equal to the heat we put out plus the work output. So that's just conservation of energy. What about the second law? Now, if it were just for the first law, we could just turn off this part down here. I mean, why waste any heat? Let's just have all the work, all the heat input turn into work. Why don't we just limit it to this? Well, if we did that, notice we're extracting heat from the heat source. Its entropy is going to go down. If that's the only change we make, the entropy of the universe would go down. This would not be a spontaneous process, so we can't do this. So we know we have to put some heat out here as waste heat so we can increase the entropy of the heat sink, and that will compensate for the entropy lost up here. So we can go ahead and analyze this as delta S universe has to be greater than or equal to 0. Now, we can make delta S of the universe as big as we want by shunting more and more heat down into this waste cycle down here. Well, if we do that, we're going to be robbing the work, and the work is the whole point of a heat engine, right? We could turn this off entirely and just have the heat go directly from here down to here, but that would be zero efficiency, right? We want to maximize this. So we can say, why don't we just make this smaller and smaller and the work bigger and bigger until we reach a point where it's just barely possible. That'll be maximum efficiency. So at maximum efficiency is when delta S universe is going to be equal to 0, right? Everything else, we're just wasting energy making it more and more spontaneous. Okay, so what is delta S universe? Well, delta S universe we know is equal to the delta S for the surroundings. Oops, my delta's not there. Plus delta S for the system. And I'm just going to leave off the subscript. Whenever I leave off the subscript, it means we're talking about just the system. Now, if we look at the system is a cycle. So the delta S of the fluid, whether it be water or something else, is equal to 0 because it's a cycle. So that means we're just looking at delta S of surroundings, but we can break this up into two pieces. We can say the surroundings is made up of the cold, the heat sink, and it's also made up of the heat source. So the sum of those two entropy changes is going to be equal to 0 if we're operating most efficiently. Okay, so I've redrawn our heat engine over here, and then the two equations. The first law that says that the heat we put in either ends up as waste heat or as work, and the second law that the entropy that we lose when we draw heat out of the heat sink has to be at least compensated for by energy we gain when we reject waste heat. All right, so let's go ahead and put equations in for these. We know that we could say that we're doing the heat transfer at a single temperature. So delta S for the cold is just going to be the heat that we put into the cold divided by the temperature. If we look at the heat source, though, we're pulling heat out. So we can see that we're going to be losing entropy from the heat source. So in other words, this is going to be a negative number, this is going to be a positive number, and we have to make sure this positive number is enough to counterbalance this entropy loss, or the system or the process will be impossible. Let's go ahead and define efficiency. Efficiency usually has the symbol epsilon. And we're going to define it as what we get out divided by what we put in. Well, what we get out is work. That's what we're trying to get out. And what we're putting in is energy in the form of heat. Okay, let's go ahead and rearrange this equation. We can see that efficiency, or the work, we come back over here, we can see work is just the difference between the two heats. So work is just the heat we put in minus the waste heat. Further, we can solve for Q cold by looking at this equation. We can see that Q cold over T cold has to be equal to Q hot over T hot. And so we can just solve that for T cold, or for Q cold. Just Tc over T hot times Q hot. And then we can plug that in right here. So if we do that, we get that the efficiency is equal to Q hot minus T hot over T cold over T hot times Q hot all over Q hot. And then we can just divide the top and the bottom by Q hot, and we get that the efficiency of a Carnot cycle is just going to be 1 minus T cold over T hot.